or I ask you to express 40 degree per second, 40 degree per second in rev per second, revolution per second, be rev per minute, and then so we have 40 degree per second to be converted to revolution per second. So when we look at this, we have 40 degree over 1 second. So we don't have any problem with the denominator. We have an issue with the numerator. And we have to convert this to rev per second. So we convert 40 degree to revolution. 360 degree is to 1 revolution. So if 360 is to 1, what will be 40 degree? Will it be more or less? Plus, that will be less.
Less.
If less, more divide. So this will be equal to 40 degree on 360 by 1 rev. This will give us 1 on 9 rev. And 1 on 9, I think, what is 1 divided by 9? 0.111 revolution, approximately 0.11. Therefore, we have 0.111 rev per second. Okay, then the next question asks that we convert this same, okay, to rev per minute. So we'll use the same thing. We can use a 40 degree, but we can also use this. We have 0.1111 rev per second. So this time the bone of contention is changing the denominator. We have 1 second. Okay, so if 60 seconds equal 1 minute, then 1 second would be is to 1 on 60 minutes. And what is 1 on 60? What is 1 on 60? Or
0.0167. 0.0167.
Okay. So we have 0.111 rev divided by 0.0167 minutes. And that must give us 6.67 rev per minute. Confirm for us. Divide 0.111 by 0.0167. Is that correct? Hello, is that correct?
Yes.
Okay. Then the next task is to convert the same thing, the same to radian per second. So I'll use this 0.111 rev per second. And we are converting this to radian per second. So we have a problem with the numerator because the denominator is okay. So if 1 revolution is to 2 pi radian, and we know 2 pi radian is also equal to 6.28 radian. So if 1 is this, what of 0.111 revolution? Will it be more or less? If 1 is given as this, 0.111 revolution, will it be more or less? Certainly it will be less. If less, then more divide. Okay, so we have 0.111 rev over 1 rev times 6.28. So multiply 0.111 by 6.28.
0.69.
0.69. Okay.
Right.
Is that 69 what?
I say, please, no, nothing.
Oh, okay. I think because we approximated. So this is radian per second. So it isn't, since it's the same thing, I mean, there's a way out. It shouldn't be anything so difficult. So I'll be sending you a lot of trials to do. Okay, different questions. Okay, on this so that you can apply to broaden your understanding. We ended at angular acceleration, right? How angular acceleration relates to linear acceleration. And what is angular acceleration? Yes, Lizzie, what is angular acceleration?
Angular acceleration is
the rate of change of somebody else. Angular acceleration is the rate of change of
the rate of change of angular velocity with respect to time.
So yes, so the symbol, please don't forget the symbols. Alpha is delta omega. Let me bring it down. Alpha is equal to delta omega over t. The rate of change of angular velocity with respect to time. SI units, radian per second, giving us radian per second squared for alpha. Now, how does angular acceleration relate to linear acceleration? Yes. How does angular acceleration relate to linear acceleration? Anybody? Len. Hello, Len.
Stadia.
How does angular acceleration relate to linear acceleration?
Please, linear acceleration, which is A, is equal to R times alpha.
It's equal to R times alpha. Thank you. And how did we do this? How did we come by this formula? How did we get this? Anybody?
Is directly proportional to angular acceleration.
Yes, it's true. Linear acceleration is direct proportional to because R is constant. But how did we come by this formula? Okay, so we picked on You know, acceleration A, linear acceleration is the rate of change of linear speed within the circumference. And then angular acceleration alpha is the rate of change of angular velocity with respect to time. So we picked on how V relates to omega, V R omega. Because a change in V with time would give us A, we divided through by T. Because a change in omega would give us this, we also divided through by T. So this side is what is giving us A, and this side is what is giving us alpha. So R alpha. Okay. Another thing to look at. When a body is in circular motion, when a body goes through one complete revolution, for one complete revolution, what is the angular displacement? For one
360.
complete, hello, what's the angular displacement?
360 degrees.
In terms of radian,
2 pi radian.
good. So this is equal to 2 pi. Here we are working in SI units, so 2 pi radian. Now what is the name given to the time taken to make one complete revolution?
Period.
That's the period. So please, the period, capital T, is defined as the time taken for a body to make a complete revolution. Okay, so the period is defined as the time taken for a body to make a complete revolution, capital T. So practically, this is like this. Lizzie is an athlete. Lizzie, I tasked Lizzie to go around this oval, go around the oval for 5 times. So number, I have 5 times. Assuming the total time Lizzie takes to make the 5 complete revolution as 2 minutes. 2 minutes in seconds is equal to 2 minutes in seconds is equal to
660 seconds.
come again, 2 minutes. 120 seconds. So you see, you used 120 seconds to go around the circle 5 times. If I want the time taken to make every one complete revolution, how do we get it? Lizzie uses a total of 120 seconds to go around a circle 5 times. If I want time for one complete revolution, how do I get it? Yes. How do I get the time for one? Anybody? Who will help me? Stephanie. Stephanie. My problem is this. She takes a total of she takes a total of 120 seconds to make 5 complete revolutions. So if I need the time taken for one, taken by Lizzie to make 1 complete revolution, how do I calculate it?
Yeah, you divide the 120 seconds by the 5 to get
Exactly.
1.
Exactly. So this will be 120 seconds divided by the number of complete. Okay. So, and this value, I think that would be what? Is it 60 seconds? Would that be 60?
24.
Okay, so 24 seconds. So this value is what we call as the period. Period. So period capital T is equal to total time divided by number of complete revolution. Okay. So period capital T is the time taken for a body to make 1 complete revolution. And it is determined by T is equal to small t over n, where big T is the period, small t is the total time, and n is the number of complete revolutions. N is the number of complete revolutions. What do you think is the SI unit of period? What's the
T
S?
inverse.
Pardon?
T inverse.
Y
It's
T.
T.
Y
It's
T.
T, sorry.
Y T inverse Y T.
Oh, Mr. Dia, T inverse is frequency.
So
And
it's
then
T
T is period.
because
Yes.
it is also time. The only difference is that this is a specific time to make 1 complete revolution. Is that okay? So the SI unit of period is seconds. Now another time to quantity to look at, frequency. The word frequency comes from frequent. So if Lizzie can use 120 seconds to make, look at the school field or the stadium. Let's be a bit exaggerative here. Look at the stadium. Lizzie can use 120 seconds to go around the Cape Coast Stadium 5 times. Hey, we'll clap for you. Oh. Okay. It means that you were very, very, very frequent. So if we want to determine your frequency, how frequent you were, this will be equal to, please, let me pick this call from school and then get back to you, okay? Very, very urgent.
Yes.
Oh, let's continue. The call is even dropped. Okay, so if we want to calculate for how frequent Lizzie, okay, is, we have to divide the number of times she made by the total time. The number of times she was able to go around it by the total time. And so frequency F is equal to number of number of times divided by total time, whereas the period capital T is equal to total time divided by the number. Can you see any connection between F and T?
Yes, please.
What is the connection? What's that connection between F and T?
No, F is the inverse of T, which is the P.
Exactly. So F is the inverse of T, or T is the inverse of F. All right. Please, is it understood by all?
Yes,
Yes.
please.
Okay, how then can you define frequency? What is frequency? What is frequency?
Sir,
Uh-huh.
sir, frequency is the number of complete oscillation made by a body in a circular motion.
Okay. More views. Another view. So Samuela, I'ma go ahead.
Sir, please. Frequency is the number of complete oscillation made by a body in a given period of time.
All right. So because this is about circular motion, we'll say that frequency is the number of complete revolutions. Oscillation is for simple harmonic motion. Here we'll restrict ourselves to revolution. Is the number of complete revolutions, okay, within a second. We purge the time for frequency, we purge the time for 1 second. So within 1 second, we want to see how frequent you can be. Move round the circular or the oval within 1 second. So we define frequency as the number of complete revolutions made within a second or within 1 second. Is that okay? What do you think? So look at something. F, we are saying that F is equal to N over T. What then do you think is the SI unit of, is the derived unit of frequency? What's the derived unit of frequency? What's the derived unit? What unit can we derive from here? Herbert.
Seconds.
Go ahead.
Mr. Dad, please, I'm not getting.
Okay, somebody else to try. Herbert and Co, come in. Yes, Adwa. Epia.
First, second.
Okay, go ahead. Stephanie, go ahead. Stephanie, go ahead. Okay, so this is, you see, number has no units. Number is dimensionless. So 1 over second. So this is per second.
Mr. T, I said it.
Mr. Dad, seconds inverse.
Oh, then you are right. Whoever said this is correct. Clap for yourself. All right, Carl, mute yourself. So the derived unit is per second. And this was honored to Robert Hertz. Was honored to Robert Hertz. And so the name, the unit was changed from per second to hertz. HZ, shortened as capital H. All right. But frequency relates to the period by 1 on T, or T is 1 on F. All right. Another thing to look at. When a body makes one complete revolution, the angular displacement is 2 pi radian. Then the time taken to make this one complete revolution is the period. If we want to determine the angular speed, we know angular speed to be equal to theta over t from 0 to this. So the change in delta theta would be equal to 2 pi radian minus 0. The initial is 0. So divided by time interval of t. Therefore, a time interval of t. But this t, the time taken to make one complete revolution, is the period, capital T. Therefore, angular velocity becomes 2 pi over the period. Or, because what we have
Mr.
here...
Dear. Mr. Dear.
Hello?
And please the change in theta, is it 2 pi minus 0 or theta?
Exactly. Look at...
2 pi minus 0.
Yes, look at something. A body is here. The initial angular displacement, omega 1, is equal to 0. When it's not moving, when the body hasn't moved yet within the circumference, the initial angular displacement theta 1 is 0. Now when it moves, let me clear it from here. Omega is the rate of change of angular displacement with time. So when the body is here, its initial angular displacement is 0. When it begins to move, goes and come back to its final angular displacement is 2 pi radian, aka 360 degrees. So if we are to calculate this is equal to 2 pi minus 0, final minus initial, divided by the time taken to make one complete revolution. This time we are calling as the period. Therefore, we have omega is equal to 2 pi on t. And this is also equal to 2 pi times 1 over t. But we know 1 over t to be f. So we also have omega equal to 2 pi f. These two are very, very important equations in circular motion, in simple harmonic motion, and in wave motion. So take note of them, these two equations. So when a body makes one complete revolution, the angular speed or the angular velocity is equal to 2 pi over the period, or 2 pi times the frequency. Please, is that clear? Let me drop a question. We are going to apply that in solving a problem. So let me take a shot of it. And drop this in the group. So as a physics person, and it's now 3:40. So an object moves around a circle of radius 3 meters with an angular velocity of 4 radians per second. So let's put the information down. We are given the radius of the circle to be 3 meters. Then the angular velocity omega is given as 4 radians per second. We are first to calculate for the frequency, I frequency. So how do we determine the frequency? Yes. How do we determine the frequency? Anybody to help us? Anybody? Okay, Lizzie.
Mr. Dia, please, I use the omega formula.
Okay, so knowing
So
omega
omega is equal to 2 pi f.
2 pi f. Yes, that's what you need to do. So f therefore would omega on 2 pi.
2 pi.
Good. So
And
omega is
4 over.
So it is 2 over pi or 2 divided by 3.142. And that will be 0.6.
37
Okay.
Per second.
So per second or hertz.
per hertz.
Yes. Then the period. The second question is the period of rotation, capital T. Capital T. Caleb. Caleb, are you there? Oh, there's no Carl. Carl. How do we determine the period? Hello, Carl. Okay. So let anybody, apart from Lizzie. Okay, Aduma, Jima. Charlotte,
Please,
let's go.
using the omega formula, but this time round, omega will be equal to 2 pi over t.
So 2 pi over t. Then you make t the subject.
The subject. So that will be 2 pi over omega.
Or
Or use the 1 over f.
exactly. Or 1 over f. So once you have f, you just put it there and that will give you the period. Or as Jima said, 2 pi over 4. And this will be pi on 2. And look at the frequency one. 2 on pi. So what did you make for the frequency? What exact value?
1.57 seconds.
1.57 seconds. Then finally, you have to calculate for the speed. How do we determine the speed? Plus, how do we determine the speed? Stephanie, do you follow?
Yes, frequency is V is equal to R times.
Thank you. So using V is equal to R omega, the relationship between linear speed within the circumference or velocity and angular speed. So V therefore is equal to radius of 3 times angular velocity of 4, which is 12 meter per second. This is a solution to the problem. Okay, let's continue. Now, just as we have equations, 3 equations of linear motion, we also have equations of circular motion. For linear motion, let's recap whatever we learned about the equations of linear motion. What's the first equation? What's the first equation? Linear motion.
V is,
Equation 1.
V is equal to
V is equal to
U plus 8.
Lizzie, you are learning in group. Conference learning. V is equal to U plus 80. Equation 2. Equation 2.
S is equal to
S is equal to
UT
UT
plus UT squared.
plus half AT squared. And then the third one,
V squared
V squared
is equal to U squared
U squared.
plus 2.
Even though we have for linear motion, we have this big 3. Sometimes we garnish the equation with, okay, average motion equation, which is not an equation on its own though, but it enables us to see things clearly. So sometimes we include this, but the truth is that equation 2 and 3 is obtained from this. So we don't really call this as an equation. Now, under circular motion, circular and rotational motion, we have similar equations. You see, for linear motion, equation 1, V is equal to U plus 80. When it comes to circular motion, this equation is seen to be, you see, this is final velocity. So we have final angular velocity, omega 2. This is initial velocity. This is also equal to initial angular velocity. This is linear acceleration. Under circular motion, we have angular acceleration. Time doesn't know circular, neither linear. So for circular motion, the first equation becomes omega 2 is equal to omega 1 plus angular acceleration times t. The first circular motion equation. Then 2. Equation 2 under linear motion. S is equal to ut plus half at squared. Each frame under circular motion is this. This is linear displacement. In circular motion, this is related to what parameter or quantity in circular motion. How would you relate this in circular motion?
Displacement.
Angular.
Displacement.
Yes, so theta is equal to u is initial velocity. We have initial angular velocity 1 t plus half angular acceleration times t squared. So equation 2, we have which is the second equation of circular motion. Then the last one, v squared is equal to u squared plus 2as. And the circular motion, this is omega 2 squared equal to omega 1 squared plus 2 alpha theta. Equation 3. So there is that similarity between circular and linear motion. And then the non-equation one, this is also represented as theta equals omega 1 plus omega 2 all on 2 times t. So these are the 3 equations of circular motion, and we'll use this to solve problems. Example. Are you ready? Hello, are we ready?
Yes, please. Yes, please.
Okay, I'm reading. The rim of a compact disc. The rim of a compact disc starts from rest. And after 30 seconds, attains an angular velocity of 6.6 rev per second.
Consider please the time again. After 30 seconds, it attains
It attains an angular velocity of 6.6 revolution per second. Calculate the angular acceleration during the time interval in calculate the angular acceleration during the time interval in 1 revolution per second squared and in radian per second squared. So you are calculating for the angular acceleration alpha in revolution per second squared and in radian per second squared. Make me proud. Agree, Aduma?
Mr. Dia.
Agree, Aduma.
Mr. Dia.
Hello, Charlotte.
Please, did you say we should calculate the angular acceleration during the time interval?
Calculate the angular acceleration during the time interval in revolution per second squared and in radian per second squared.
Yes, please. Thank you.
So try it. Try it for about within 2 to 3. Whilst I look for another challenging work for you. Are we through?
No.
What to do? So we are told that the rim of a compact disc starts from rest, and after 30 seconds attains an angular velocity of 6.6 rev per second. Calculate the angular acceleration during the time interval in rev per second squared and then in radian per second squared. So what are we given? We are given the initial angular velocity. We are told it starts from rest. Similar to those terms, okay, we see in linear motion, start from rest, comes to a stop, or come to rest, those terms. And then the final angular velocity, 6.6 revolution per second. So its angular velocity is increasing within the time interval. The time interval is 30 seconds. So these are what we have. Once you have these details, you look for the appropriate equation out of the three. We can really solve this. So out
the
of the
equation one.
the obvious one is equation 1. Okay, so 3, we have equation 1 is omega 2 is equal to omega 1 plus alpha t. Alpha therefore is equal to omega 2 minus 1 over that. The final angular velocity 6.6 revolution minus 0 over 30. And this will give us the angular acceleration in revolution per second squared. What is 6.6 divided by 30?
0.22 rev per second square.
So 0.22 rev per second squared. And this answers the first part of the question. The second part of the question, I can use the same results to do it. Alpha, I'm to find alpha this time in radian per second squared. So alpha, which is equal to 0.22 rev per second squared. Meaning I have no problem with the denominator. I have an issue with the numerator. So I must change 0.22 revolution to radian. How do I do it? We know 1 rev is to 6.28 radian. So if 1 rev is this, we have 0.22 rev. Will it be more or less?
Less.
If less, more divide. So 0.22 over 1 times 6.28 radian. Multiply 0.22 by 6.28.
1.38 rev per second squared.
1.38. This will be radian. 1.38 radian. Therefore, alpha would be equal to 1.38 radian per second squared. How many of you got this correct?
Say me.
Okay. All right. Okay. Okay. Another way to handle the same problem is that, you see, alpha is omega 2 minus omega 1 over t. Omega 1 is 0. So change 6.6 rev per second to radian per second. When you divide by 30, you are good to go. All right. Another question. I'm sending a couple of trial works to you. And I'll draw your attention to the one to answer. So it's been sent. You are to look at question 9.25. The rest you try. Question 9.25. A wheel revolving at 6.00 revolution per second has an angular acceleration of 4.00 radian per second squared. Find the number of times the wheel must make to reach 26.0 rev per second and the time required. Question 9.25. A wheel revolving at 6.00 rev per second has an angular acceleration of 4.00 radian per second squared. Find the number of times the wheel must make to reach 26.0 rev per second and the time required. In fact, the answers, we have the answers there. The answer to the number of times, we have 502 rev. And then the time is 31.4 seconds. But you must work, okay, to obtain it. Start work. Let's see how you are going to work towards to the answer. So look at whatever the question gives you and you pick the appropriate equation out of the three equations of motions there. All right, so about 3 minutes. Okay, so 9.25. A wheel revolving at 6.00 rev per second. So let's extract the information given. Omega 1 is equal to 6.00 rev per second. Has an angular acceleration of alpha is 4.00 radian per second squared. Find the number of times the wheel must make to reach an angular speed of 26.0 rev per second and the time required and t. So it is obvious, since we have omega 1 alpha. Let's look at what we have to look for again. Find the number of times the wheel must make. What does it mean by to determine the number of times? What does it mean by that question? We are to find the number of times. What does it mean?
Say the frequency.
Frequency. Frequency. Okay. More views.
Circumference.
Pardon?
Circumference.
Circumference. All right. So here it can also represent, to say frequency, you are not wrong. But we don't know the time. Okay. But if we are able to determine the angular displacement, we are also looking for the number of times. And this is the reason why. This is the wheel. If it starts from here and it makes one complete revolution, 1 revolution, 2 revolution, 3, on and on and on. So each revolution, 2 pi. And this is equal to angular displacement. So if I could get n number of complete revolution, it is equal to n times angular displacement. So over here, because we don't have the details of how to find the frequency is per second, and we don't have that information. And so the angular displacement theta would qualify for the number of turns. Herbert, is that okay?
Yes, sir.
Adama?
Mr. Dia. Mr. Dia, please, with the information given, can't we calculate for the time using the first formula?
You can. You can. But let's find theta first. Let's find theta. So, because we have omega 1, 2, and alpha, we can use omega 2 squared is equal to omega 1 squared plus 2 alpha theta to find it. Okay. Omega 1 is 6 squared. Omega 2 is 26 squared. Omega 1 is 6 squared plus 2 times. Here we can use this value for alpha because it is given to us in radian per second squared. The angular velocity are in revolution per second squared. So if you don't convert and you use this direct, you are wrong. So convert angular acceleration of 4 radian per second squared to revolution per second squared for me.
Sir, please, you get 0.637.
0.6
637.
revolution. Let's confirm. So if 1 rev is to 6, or if 6.28 radian is to 1 rev, we have 4 radian. Will it be more or less? Will it be more or less?
Less.
So if less, more divide. So 4 divided by 6.28 times 1 rev. And divide, let's see, divide 4 by 6.28. Is it equal to this?
You get 0.637.
Okay, so she's right. So this is rev per second squared. So 0.637 theta. Then we make theta the subject. So 26 squared minus 6 squared over 2 times 0.637 is equal to theta. Calculate for theta. What did we get for theta?
504.
Is it the same answer there? Five zero what?
2. It's 502.
This is the number of turns, meaning it will go round for angular velocity to change from 6 to 26, okay, at a uniform angular acceleration of this, the number of turns will be 502 revolutions. The time we can use omega 2 minus omega 1 divided by alpha, as said by Akwiadoma. So what is omega 2? 26 minus 6 divided by 0.637.
$31.4.
Come again.
31.4. 31, 31.
3-1. Please, are we okay with the solution?
Yes, please.
No, please.
What's the problem? Charlotte, what's the problem? Hey, Charlotte, you said no, please. What is the problem? All right. So I leave the rest of the questions. You see, I sent about, I've taken 1, 2, 3, 4, 5. As many.
Sir, please, I used the other formula and I had 504. So I wanted to know if it's wrong.
Which one
For
did you
the
use? Give me the
theta
formula.
is equal the theta is equal to, in a bracket, W2 plus W1 all on 2, all multiplying T.
And then you determine this first, right? You determine T first.
Yes, please.
Oh, it's correct. The difference, you see, the difference has to do with the approximation.
Okay.
Okay.
Yes, please.
The difference simply has to do with the approximation.
Yes.
And it will come from the time. It will come from the time because you have to change the angular acceleration to rev per second. Okay, you may approximate values and all that, and that's what account for the difference. Charlotte.
Yes, please.
Charlotte, your hand is up. Okay, so question 1, 23, 24, 26, 27. 27, we are here to treat it. So leave 27. I'm giving 23, 24, 26, okay, to you to try. And I will demand feedback on question 24 and 23. So take note of your assignment. Question 23 and 24. Yes, the answers are there, but I want to see how you work to the answers. Charlotte.
Mr. Dia.
Your hand is up.
Please, if I'm right, are you trying to say that the number of turns in this question is equal to the angular displacement?
Yes. And that is the demonstration I gave you. You see, if the body makes one complete revolution, 1/10 or 1 revolution, 2, 3. So the number of turns, and don't forget, each turn has to do with and the angular displacement equal to 2 pi or 1 revolution. So if I go once, 360 or 2 pi or 1 complete revolution, 2, 3, 4. So if I find theta, I have also found the number of revolutions. Okay, so per
Yes.
our answer, we had 502 rev, meaning that the wheel makes 502 complete revolutions for its speed to move from 6 to 26. That is what it means. All right. The next thing I want us to look at is centripetal force. Centripetal. The word centripetal force or centripetal is a Greek word which means center seeking. Centripetal force. And centripetal is a two word meaning center seeking. So centripetal force is a center seeking force. It's a force which is always looking for the center of what? The circle. In JHS, you were taken through centripetal force and centrifugal force, right? So if I ask you what centripetal force, I'm sure you have something to tell me. Carl, what is centripetal force?
Centripetal force refers to the force which pulls an object in a circular motion to the center of this one.
Of the circle. Yes. Thank you. So whenever a body is in circular motion, its ability to stay within the circular path is by the aid of a certain center seeking force, which we are talking about. So let's look at situations of a body staying within a circular path. One, when an object is tied to a string, objects tied to a string and weld. Once the stone or the object stays within a circular path, then it means that there's a certain force which is pulling the object towards the center. Another situation of circular motion, when a body or a car negotiates a bend, there must be a force which pulls the car towards the center of the bend or the circle, aka roundabout. 3, motion of electrons. Motion of electrons around the nucleus. Around the nucleus. Okay, around the nucleus. Yes. This would also need a certain force to keep the electrons within the atomic shells. And the fourth situation is motion of planets around the sun. There will be centripetal force. So what is centripetal force and what causes it? The truth is that centripetal force seems to be a non-existent force. It looks to be non-existent because centripetal force is always provided by something within the same system. So when a body is tied to a string, example, stone, tied to a string and well, the centripetal force F, we say, is equal to the tensional force within the string, or force of tension within the string. So look at something. The stone must stay within the circular part, but that centripetal force which enables it to stay within the circular part is supplied by the tension within the string. That is why when an object is tied to a string and it breaks, the string breaks, the body fails to stay within the circular part because the tension is gone. The tension which supports the object is gone. And so the body would just move away and wouldn't stay within the circular part. 2, a car negotiating a bend. In the case of a car negotiating a bend, the centripetal force is provided by the frictional force between the road and then the tire. So this is equal to frictional force between the road and the tire, the lorry or the vehicle tire. So in this particular instance too, centripetal force is being provided by something. Then motion of electrons around the nucleus. And in this particular situation too, the centripetal force is also provided by the electrostatic force of attraction between the electron and the nucleus. That electrostatic force of attraction between electron and the nucleus. Then motion of planets around the sun. The fourth point, the same centripetal force is equal to, this is provided by the gravitational force of attraction between, the planet and the sun, or the gravitational pull, gravitational force of attraction between the planets and the sun. And so that explains what I said, that centripetal force seems to be a non-existent force because within the system, it is always provided by something else. As for the pair, The other pair, centrifugal, we don't even talk about it. That is even a false prophet. Please, are we okay? Class, are we fine?
Yes, please.
So these are instances of circular motion and what actually provides the centripetal force. Instances of circular motion and what provides the centripetal force. So we'll go into the nitty-gritties of centripetal force. Please, if you have any question, quickly ask. The concept of centrifugal force comes in this way. And it comes up from Newton's third law of motion, that forces move in pairs. For every action, there must be what?
An opposite and equal.
Yes. So all that they are saying is that if this is a body, we expect centripetal force to pull it towards the center. This is the center of the circle. If forces move in pairs, then once there is an actional force, centripetal, then there must be a reactional force, centrifugal. So this is what brings about centrifugal force. But investigation has shown that if an object is tied to a body and is being whirled, okay, the object stays within the circular path. But the moment you cut the string which supports the body, when you cut the string, the centripetal force is also cut. It's not there. If the centripetal force is not there, then we expect centrifugal force to take over. So the moment the string is cut, this object is expected to be thrown in this direction. It's expected to be thrown in this direction because the moment the string is cut, which eliminates the centripetal force, we expect the fugal to take over. And so the object is expected to be thrown away horizontally. But it doesn't happen that way. When an object is tied to a string and you cut it, the object moves in this direction, a direction tangential to the circle, either in this direction or in this direction. So the question is that if there is a centrifugal force, which is opposite and equal in magnitude to the beta, where are you? Where then is the object moving tangential to the circle and not in the direction of the centrifugal force? This is the application which defeats centrifugal force, but it is there because of Newton's third law of motion. Newton's third law. Please, are we okay? So centripetal seems to be a non-existent force. You say it's a hypothetical force. As for fugal there, it is not talked about. All right. So let's go into how to calculate for centripetal force. This is a body in circular motion. The body moves from a point A, and within a time interval delta t, small time interval. The body moves from A to B. This is the linear displacement, small linear displacement, delta S. It takes small time delta t to move from A to B. This linear displacement delta S corresponds to an angular displacement at the center. Small, this is delta theta. When we take delta, it means we are looking at small quantities. Okay. Now, when a body is in circular motion, please, and here we are looking at uniform circular motion. And when a body is in uniform circular motion, what it means is that the body is expected to move with a constant speed, v. I said this in our first meeting. But then, a body in circular motion has its direction always changing. And this is it. Let me draw a different circle to explain the changing direction. When the body is here, it's here, and finally here. When it's here, this is the direction, and here we are looking at it moving in that anti-clockwise. Okay. When it gets to this point, this is its direction. When it gets to this point, this is its direction. When it gets to this point, this is its direction. Its direction. So a body in circular motion has its direction constantly changing. Has its direction constantly changing. So when the body is here, this is the direction of the body. When the body gets to B, this is the direction of the body. This body is supposed to move in with constant velocity, uniform circular motion. But due to its changing direction, its velocity at every point changes. So when it is at A, this is the velocity VA. When it gets to B, this is the velocity VB. So we expect the body is expected to move with constant speed. But it doesn't happen. But due to its changing direction, its velocity at every point also changes. This is the reason for which we have VA and VB. Now, what is velocity? We define velocity as the rate of change of displacement with respect to time, or velocity also is talked about when speed is constant, but we have changing direction. So that is the situation we have here. Though the speed is constant, but due to the changing direction, we have different velocities at different points. Meaning, if we have a third position to consider, this will also be VC, VD, because of the changing direction. Please, are we okay?
Yes, please.
So we are having the velocities, even though the body is expected to move with a constant speed, but due to the changing direction, we have changing velocities at every position of the body. A has velocity VA, B has velocity VB. Now, these velocities, we say is tangential to the circle. As for physics and our terms, we'll talk about them. VA is tangential to the circle, and this is what we mean. If a velocity is tangential to a circle, it means that if this is the radius, R, well, the velocity is here, V, it means this velocity is perpendicular to the radius. So a tangential velocity is such that the velocity here, the linear velocity is perpendicular to the radius, of the circle, and that is what is happening to VA. VA is perpendicular to this radius, and then VB is also perpendicular to this radius. And when the body is in circular motion, actually that is what happens. Its linear velocity is always tangential to the circle. Okay, so it's 4:50. In fact, I will leave it here. We'll continue on Friday. But please, your task is as I assigned to you. You are to look at question 1, 23, and 24. Do it and send your answers. Please, the number of marked assignment I had wasn't interesting at all. If it continues like that, in fact, I'll report to your parents. I beg you. Don't let me report you to your parents, okay? Do it, try it, and then give me a feedback. Class,
Okay,
is that
sir.
okay?
Yes,
So,
sir.
our next meeting is on Friday, and so I'll be expecting it. Okay? Take care of
Okay,
yourselves, and in
Sir, when
fact,
should we submit it?
it can be before Friday.
Okay, sir.
All right.
Bye.
Before Friday. All right. So, class, bye-bye to all of you. I'll be expecting your feedbacks, right? If you have any question, you can WhatsApp to me and I'll give you feedback. I'll respond to your
Okay, sir.
questions.
Yes, sir.
Okay. Yo. Bye-bye.
All right, sir.
Bye.